So last class we went over the notes, the concepts. Today I want to just rehash. It's more of problem solving. Like how do we use the equations differently for these types of problems than what we did with horizontal launching? And I kind of went over that a little fast last class. So I want to take a little bit of time to go over the different things that we could calculate and how we use the equations for the basic angle launching problem. And so it's right looking like this. There's no, first off, we have to know the initial velocity. We have to know the angle, and then there's no elevation change, right? That's what I would consider the most basic angle launching problem before we get into some of the different variations on Friday and next week, Wednesday or Friday. And so just to kind of rehash, step one, right? Again, I stole this off something on the internet, right? And so they didn't have the initial velocities there, but it doesn't really matter. If we know the initial velocity and we know theta, right? These are given. Now, on Friday, I'm going to show you what happens because that's not always the case, right? But for the basic problem, it is. And then we need a way to solve these problems if one of those values wasn't given, and that's what we'll look at on Friday. But for right now, for the basic problem, this is given and this is given, and this is true, right? This is an important idea, meaning no elevation change. So if we know this and we know this, right, from trig, we know that cosine of theta, right, is VOX, the adjacent over the hypotenuse. So VOX equals VO cosine of theta. Now, hopefully you don't have to memorize that. Hopefully you know the right triangle trig well enough that you know sine, cosine, tangent, because that's all we need to know. And if not, I would just say, let's learn it so that you don't have to memorize these things and you can figure it out if the problem throws you a little curveball and you have to do something different, especially when we get into forces. And then sine of theta is opposite over hypotenuse, right? And so VOY equals VO sine of theta. That is your first step. Find this and find this. Calculator must be in degrees always for physics. Okay. Now, after that, right, we usually, when we didn't have to do this as our first step when we had the horizontal problems because the velocity was Vx and we knew VOY was 0. So our first step was always to find time. Time is always the key to these problems. And so it's our step 2, right? Because we've now found VOX or Vx and Vy. So now we need to solve for time. So it depends on what else might be given, right? If this is given, right? And if you look at the problems, you'll see usually that's the unknown that you're trying to find. But sometimes it's going to be given. And so if that is ever given, then we want to use the x equation, right? This is our easiest equation. Remember, because the horizontal velocity is always constant, we can use either one of these variables. But this is the main equation, right? For x, it's the only one we use. And then you want to solve it for time, right? And we, just like we did previously for the horizontal launching, that's all we had to do, right? So we solved for this in step 1, and this was given, so now we can find time. And that's going to give us the total time, right? That's always the easiest way to go. But if dx is unknown, well, then we have to look at the y equation, right? And so we used the y equation before. Most of the time, you're using the y equation, right? When we did horizontal launching, this was equal to 0. Well, we know that VOY, right, is not equal to 0, and it is equal to VO sine of theta from step 1. So we know that's not 0. We know G is not 0. We're looking for time, but this is the key, right? This is equal to 0. So now we get to this point right here, right? It's a quadratic equation, but there's a 0 here, so we don't need to use a quadratic formula. And so hopefully it's the other, you know, I always think of like GCF and LCD from algebra, you know, least common denominators and greatest common factors, but it's factoring, right? It's that algebra 1 skill we learned at factor. We factor out a t. And if we do that, right, and then we divide both sides by t, but so basically it tells us one of the answers is t equals 0, which we already know that. When is the projectile going to be on the ground? It's going to be on the ground right there, and it's going to be on the ground right there. This is t equals 0. So that's one of our answers, but we already know that. We want the time for it to get there. So that's why we can get rid of the time by dividing it over, right? And so we have VOY plus 1/2 GT. If I solve for t, right, subtract this over, multiply by 2, divide by g. And we get this result for time, right? And so the key to using this method of solving for time is A, remembering that this is 0. And then when you get to this step, you have to factor out a t. Sometimes maybe it's easy if factoring something you forget about, maybe you just look at it and you're like, well, I'm solving for t. I can divide everything by a time, right? Because then it's this anyway.
What?
Now, just like when we threw an object straight up in the air and it came straight back down, I showed you 3 different ways to solve for time. Now, this is the main way. If you look in Projectile, if you Google or you look online, you look in a textbook, this is kind of the main way to solve for time for these kinds of problems. But if you remember when we did the straight up and down problems, this was one of the ways of doing it, but it wasn't the main way to do it. We used this equation, right? And so if you went back to like the beginning of December and looked at your notes for when, you know, you've thrown an object up and it goes up, hits its highest point and then comes back down and you catch it right here. I think I used the coin toss as an example. We used this equation to solve for time. We could have used what I just showed you, and some of you did, but a lot of us use this to solve for time. And why did we do that? Well, because one of the things we talked about was that at the very top, the final velocity is 0, right? The initial velocity here is the value that we're launching it up with. And so if we make this equal to 0, because whether it does this or if it goes like this, right? The Vy value at the top, we talked about this last class, is also 0. Vx is not 0, but Vy is 0 at the top, whether it's here or whether it's here, because it's got to come back down. It's got to stop for that second to come back down. And so, right, if I use this, subtract that over and divide by g, I get that for t. But if you remember when we did this, this was the version of solving for time where it only gives you the time for it to go up, right? And so we had to double it to get the total time. We had to take 2 times this value to get the total. Now, if you look at this and you look at this, right, it's exactly the same. Right? And so we're just using the other equation, using it a different way. But the key was you had to remember that this only gives us the time up, right, here or to here. And then we got to double it because as long as it's coming back to the same height that it was at, it takes the same amount of time to go up as it does to come down. Then there was a third way. Right now, again, I wouldn't go with trying to, you know, learn all 3 ways. Pick the way that you think is the easiest way to go and then use it. But the other way was the fact that we know if this is launched upward, when it comes back down here, that Vy here is going to be the same as Voy there. And so Vy is going to be equal and opposite to the vertical velocity at launching. And so what happens is if I use this equation, right, so I'll just kind of rewrite it here. But in for Vy, I put this because we're saying right? We found VOY by VO sine of theta. Well, we know if it comes back down, the vertical velocity here is going to be the same. Right, so if this was 30, this is going to be negative 30. And so now by substituting in, just using letters, when I substitute this or subtract this over, I'm going to get 2 VOY, right, equals GT. Divide both sides by G. Right, and I get the same result again. Right, and so you have 3 different ways to solve for time. Now, again, if you try to learn all 3, you're probably going to get confused on something. And so I would just say, you know, does one of these 2 methods make the most sense to you? Right, this gives me the total time. Right, this gives me the total time. I don't have to do anything to it. I just have to remember that whatever this is, Vy is equal and opposite. Over here, I have to remember that I'm making this equal to 0. Where does that occur? That occurs at its highest point. So whatever time I get, I have to double it, right? And then the other method uses dy equaling 0. Now, once we've solved for time, right, then we can look at, well, what else might we solve for? And, oops, sorry. One of the things that we talked about last class was finding that maximum height. And so depending on how you solve for time, if we know the ball lands here distance away, that's the horizontal distance. But if we wanted to know this point, right, what is dy max, right? We know this occurs at halfway for time, right, and halfway for the horizontal distance, right? If this was from here to here is 100 yards, this is going to be 50 yards. So we don't need the distance. The distance isn't going to help us, but the time is. If it takes 10 seconds to land here, it means it's going to take 5 seconds to get to its highest point. 5 seconds to go up, 5 seconds to come down. So when I use this equation to find dy max, right, the maximum height, you don't have to label it like this. We know this, right? We solved for this. Again, VOY will equal VO sine of theta, what we did in step 1. But when we put in time here, we have to put in half of the time, right? Half of the total time. And then when you put in G here, you have to remember to make it negative. That's one of the mistakes, is forgetting to make that a negative 10. And then this T again is whatever the time was divided by 2, and then you square it. This will tell us this value. Now, I showed you this back when we did, again, the straight up and down problems, but it wasn't our go-to method to do that. And so while you can use this, again, the key to remembering is that the maximum height occurs at 1/2 the total time. Right? I think it's common sense, but when sometimes these things that are common sense, when we're solving problems, we tend to forget them. And so what if we don't want to use time at all to find the maximum height? We could do that if we go to this equation. And this was our go-to equation, again, when we had something go straight up in the air, hit its highest point and come back down, because at the top, we said Vy is equal to 0. So again, the vertical motion of that or this is identical. And so we know at that point right there, Vy is still equal to 0, and we can find this dy value without having to solve for time using this equation. We make this equal to 0. Right, and now if I solve that for this, and you can label it like this, or you can call it dy, or you can call it dy max, right? It's whatever you prefer to use there. But I'm going to subtract over and divide by 2g. And that gives me the dy value equals negative VOY squared. Let's get away with having this work well today. Divided by 2g, right? And so this is how we could find that maximum height. And when we did this, if you looked at your notes, you would see this. right? We would have started with the same equation. We didn't have y's because we weren't doing two-dimensional motion, so we didn't need x's and y's to keep track of it. But you would look at your notes and you would see, define this height right here, this is what we did. Or we used the equation for time. And so it still works, right? Because the vertical motion is the same regardless. So you have two different methods to solve for the maximum height if the question asks for that as the unknown. Again, pick the one that makes the most sense to you. And then the last one, which is the easiest one, is what if dx is the unknown? Oops, sorry. Right? Instead, so we obviously didn't use this to solve for time. And again, remember that Vx is going to be VO cosine of theta. So we would have already calculated this in step one. If I solve for dx, it is simply Vx times time, right? And we always use total time, right? That's the same regardless of what kind of projectile motion problem we're doing, right? The x is always the same. So we always can count on x being the same each time. Any questions on the problem solving, right? It's helpful to understand how we use the equations, but sometimes it makes a lot more sense once we actually do one. First slide, meaning step one. Is that good? All right, so hopefully that helps kind of understand how we can use the equations. Again, you have some choices when we're solving problems. Sometimes maybe the problem will dictate which way is the way to go, which is easier to go. So I picked a couple problems to do. We'll see how far we can get. This was a real movie, by the way. If you have Netflix or any of that, History of the World, there's a Mel Brooks is kind of like the 60s, maybe 70s, kind of Will Ferrell type comedy. He made two of these movies. They're kind of funny. I think you're old enough. I don't know what they're rated, but so it's a real thing. So they used a Peasant pulp. They're launching him at 35 degrees at a speed of 42, right? So that speed is VO. We've got the angle, right? The Peasant lands at the same height he is launched from. So that kind of, so it looks like this too, right? In real life, they do these probably at carnivals, right? That's a cannon launching a guy into a net. Hopefully they've calculated where the net should be. Otherwise that guy's gonna have a headache, right? And so basically this is what we're looking at. A basic problem goes up, lands right here, starts right here, right? So that delta dy is equal to 0. We know the initial velocity is 42. The angle is 35, right? And so these are the three conditions for the basic problem. And so the homework for Friday, you're going to be given initial velocity, you're going to be given the angle, and regardless if it's obvious or not, it should be obvious from reading it that this is equal to 0, right? And so what do we do first? Well, we find VO x and VO y. Now you don't need to make the triangle, which you could do if that helps, right? You could do this and make this triangle each time. All right, but hopefully you'll just get used to doing this and you'll be all right. VOX is equal to VO cosine of theta. So 42 times cosine of 35. Again, your calculator needs to be in degrees. That's one of the big mistakes, especially if you guys had a math class like prior to physics and you don't realize that it's not, and all your answers look much, much different. So 34.4, I would always round it to the nearest tenth, if not whole number. VOY is equal to its opposite, right? So it's sine VO times sine of theta. So 42 times sine of 35, 24.09, so I'd round that up to 24.1. Right, so that's the first thing I want to do for every angle problem. Now I'm trying to find time, right? So I've shown you 3 different ways to solve for time. Again, it doesn't matter which method you use. So for part A, we're looking for t. You can use this equation. Right, or you can use this equation, and you have 2 different ways to use it. Just give me a thumbs up. How many of you think you would use the first equation? How many of you think you would use the second equation? Okay. Looks like most of you. So I'll do this one on this problem. How many of you would make Vy equal to negative 24.1, or how many of you would make it equal to 0? Let's say, how many of you would make this equal to 0 to solve for time? A couple of you, all right. So you can still solve this for time, right? And not make anything 0, and then kind of decide afterwards just by doing that. And then you could make that equal to 0 or not. If you don't make this equal to 0, you have to make it equal to 24.1, but negative. I didn't leave myself enough room, so I'm not going to write the unit both times. Right, and so it should look like this if this is not 0. And then the other key is, right, g has got to be negative because we can't end up with a negative value for time. So this gives me negative 48.2 over negative 10. Right, the negatives cancel. And I would just call this 4.8 seconds. So if you got 2.4, you would, right, by making this equal to 0, because you'd have 24.1 over 10, which is 2.41, you'd have to double it to get 4.8 the total time. Let me just show you what this looks like in case you're going to do that. Right, VOYT plus 1/2 GT squared. I'm going to factor out a t here. Solve this for t. I'm going to subtract this over. I'm going to multiply by 2. I'm going to divide by g. Right, and then when I plug it in, there's that 2 that I would, if I had made this equal to 0. And I get 4.8 seconds again, right? So either way works. Now for part B, it says how far away did he land? So we're looking for this distance, right? We're not looking for the maximum height, which would occur there. It didn't ask for that. And so that's our easy one to do because the x equation is, right, the one we can count on being the same every time. We don't use it differently. There's only 3 variables. Nothing can ever be 0. And so the math is what we've been doing. We take Vx and we multiply it by the total time. Right, and that's why we need this number. There's a really big lag with me writing and this thing showing up. So 34.4 times 4.8, 165.12. And that's where it lands. Right, and so that's a basic problem where it asks for time and asks for the horizontal distance. Now, part C, determine the speed of the peasant as it hits the ground. So this is one of those things where you'd be like, well, that was a trick question, right? If we know the initial velocity is 42, and we solved for Vx and we solved for Vy, we know that Vx is going to stay the same the entire time, even at the highest point, right? When this is 0 for vertical, Vx is still 34.4. Then on the way down, Vx is constant, but Vy is increasing. And when he hits the ground right here, right, what is V? That's what it's asking for. Well, V is going to equal the initial velocity, right? And so it was 42 for the initial velocity, VO. V is going to be a negative 42, right? Because he's going down, right? If we looked at Vx at this point, it would be 34.4. And if we looked at Vy at this point, it would be a negative 24.1, right? Because he lands at the same height that he was at. Any questions on that problem? Okay. Well, like I had 4 of them set up, and that took like 15 minutes. But there's other versions of these, and so I want you to see a different type of problem. And then I had a couple kind of of similar to what we did, so that you guys would have been able to do them kind of on your own. So let me try to do one more and see where that lands, because this one's a little bit different than the last one, and only because it gives you different information. And so here you see a rugby ball is kicked towards the goal. These are the goalposts for rugby. It's similar to football. The ball passes over the crossbar. This is the crossbar between the 2 posts. It takes 1.5 seconds, right? So this is different because it gives us time, which is kind of a game changer with whenever time is given. To reach a point vertically above the crossbar of the post. So right here, right, I know it's not a side view, but when he kicks it, it goes up, hits its highest point right there, because it tells you the ball reaches its maximum height the same time it crosses over or passes over the crossbar. So it takes 1.5 seconds to get from here to here, which means on the way down, right, wherever that lands, from that point to that point, it's going to take 1.5 seconds, right? So we know the total time is 3 seconds. So that's why it's completely different than what we just did. But then it asks us to calculate some of these other things. But notice we weren't given, right? We weren't given the initial velocity, and we weren't given theta. And so that's why I wanted to show you, it's still a basic problem, but we don't need anything new. This is still true, because we're, I know this is kind of like a side view problem, but right, the ball's going to hit over here. And if it goes from here to here at its highest point, and that's 28 meters, that means this also is going to be 28 meters. If this is 11 meters at its highest point, this has got to be 28 meters, because it tells you, right, it reaches its maximum height the same time it passes over the crossbar. So it says calculate the ball's horizontal component, VOX. So what you would probably think of and be like, all right, well, Doc said to do this, but do we know this? No. Do we know the angle? No. All right, so what's up with that? So I can't use that. But what else do we know? Well, we know that VOX equals VX, right? It's constant. But it equals, it equals DX dx over time. So do we know a dx and a time, right? And we do, because we know that where the rugby player kicks the ball is 28 meters from the goalpost. And we know that it takes 1.5 seconds to get there. So we have a distance that goes with a time, a horizontal distance that goes with a time. And so we can use that to solve for Vx. I get 18.6 repeating. So I'll just call it 18.7 meters per second. Then it says calculate VOY, right? The vertical velocity. So again, you should think, all right, I want to do this. But again, for the same reasons, we can't, because we don't know VO and we don't know the angle. So this would mean I want to look at using one of the VY equations, right? Not the one with distance in it, but one with VY squared, but the one with time in it. And so looking at this equation, we know that at this point right here, when the rugby ball gets there, that's at its highest point. Can I change myself saying that this was working in my, oh, no, that's not, that's unfortunate. All right, so I want to use, I can rewrite some of this again. We know that at its highest point, Vy is equal to 0. And so I know that's equal to 0. Now, instead of solving for time like we did on the last problem, we're going to use this to solve for Voy, right, by subtracting this to the other side. Right, there's a negative sign, but G is also negative. So that gets rid of that force. And we know that the time for it to go from here to here was 1.5 seconds. And so that gives me Voy being 15 meters per second. Right, and then I'm going to need this value, so I'll just write it right here, I guess. Vx was 18.7. So now we found Voy, we know Vox, determine the magnitude of the initial velocity, right? And so this is what we did for the horizontal, like when projection, when we were trying to find the resultant speed at impact, right? This is where Pythagorean theorem comes into play, right? We've solved for this. This is 18.7. We solved for this. This is 15. Make sure I hit erase all of it. Voy, here's theta, right? And so we don't know theta, so I can't use trig, but I can use Pythagorean's theorem because I have the two sides. I've solved for them, so I can solve for the initial velocity by taking the square root of both sides, right? That was 18.7. And that was 15. So use Pythagorean's theorem, 18.7 squared plus 15 squared, 573, take the square root, 23.946. So I'll just call that 24 meters per second, right? And so that's VO, right? Like the last problem that was given, that was the value given. We found VOX and found VOY. So it's just showing you a different way of doing that. You're still using the same concepts, but just a different approach. And the last part says determine the angle. So that means I want to know what this is. So for that, I'm just going to use trig, right? Because we know what this is, we know what this is, we know what this is. I like using tangent, but it doesn't matter. You can use sine, cosine, or tangent. Tangent is opposite over adjacent, right? Which was VOY was 15, VOX was 18.7. You can put the units, right? But they're going to cancel off anyway because they're the same unit. But to get theta, you have to do the inverse trig function. Again, make sure your calculator's in degrees when you do this. And I get 38.73, so I'll just call that 38.7 degrees. Right, now we don't have to solve for dx, like where does it land? We know that it's gonna land at 56 meters, right? Because if it goes from here to here in 28, it's gonna land over here, right? 28. We already know the maximum height is given as 11. So we could have used, to find VOY, we could have used, I know that looks like 1, but we could have used the Vy squared equation, but I think using the time one was easier because we knew that it took 1.5 seconds to reach its highest point. So this just kind of shows you, still a basic angle problem, and it doesn't quite fit. Okay, VO and theta were not given, but we don't need what I'm going to show you on Friday to solve this problem. Okay, let me start this problem just so that we're finish it here. So keep kind of plugging along, and then you can kind of check your answers since you should be well ahead of me. So VO is 20. theta is 40. dy equals 0. So I'm going to find Vox. I'll find that first. So that's 15.3. VOY. Twenty times sine of 40, 12.9. Right. So, and again, you might find, depending on what equations you use, might not even need both of those. But I would just say, as a good problem-solving habit, do that first. It kind of gets the ball rolling and kind of gets you heading somewhere. Now, if I'm going to find the maximum height without time, which I think is the way to go, just because it's what we did before, and hopefully you kind of remember those steps from before. And so, at least for this problem, I'll do it using this equation. Right? What is this maximum height? You could call it h if you wanted to also, but the key is remembering that Vy equals 0 at the maximum height. Right? This is equal to 0. If you're going to use this method, this equation, subtract this over, divide by 2g, right? That's going to equal dy. And so here's the, if you get this far, a lot of times people forget and they put in 20 here, but we need the 12.9, right? That's the velocity that's taking it up. And we need the negative 10 because there's a negative there and we need those to cancel. All right, I get 8.3, 8.26, so I'll call it 8.3 meters. Right, so that's how high it goes right here. Now I need time, right? And I'll kind of go with this method since a lot of you said that earlier. Again, depending on if you make that 0 or not, and a lot of you might, if you did use this equation, you might be kind of in that mindset, being where that's 0. So I'll just kind of do it this way. Solve this for t. Right, but remember, because I made that 0, that's only going to give me the time for it to go up. It's 12.8, right? 12.9 over negative 10. Right, the negatives cancel, so it gives me 1.3 seconds up. So I double that to get the total time, 2.6 seconds. Right, because this is the time for it to go from here to here, so 1.3 to go to there. How far away does it land? Right, again, it's the nice thing about this is that for x, it's always the same, right? I've said that a lot. X is always the same. That is an x, even though it doesn't look like one. Solve for dx. It is Vx times time. It's 15.3 times 2.6. Didn't give myself enough room again. Right, so 15.3 times 2.6, 39.78, so 39.8, you could round it to 40.